Along with substitution, integration by parts is one of the most important techniques that you will encounter when you're dealing with integrals. Chain rule for differentiation is the basis for the substitution method that we learned about. And what we're going to find out today is that integration by parts is essentially the equivalent of product rule, but for integration. It turns out we can derive a formula for dealing with the integral of a product of functions by looking at the formula for dealing with the derivative of a product of functions. This is how we do it. We write down product rule and we try integrating both sides. If you want to pause and have a go for yourself, this would be a good opportunity. See what happens when you integrate both sides with respect to x and move things around a little bit. Here's what we should end up with. Now, if you integrate the left-hand side, because the left-hand side is a single term, which is itself a derivative with respect to x, everything kind of cancels out and you get right back to uv. On the right-hand side, you've got two separate terms, each of which is a product of u dv by dx or v and du by dx. So it's two things multiplied together. Now, the two separate bits that are added, they can be separated out. We can treat it as two different integrals on the right-hand side. So on the left, we just have uv, the integral of the derivative of u times v. And on the right, we've got two different integrals, both of which are related to u and v, but they involve either the original function and the derivative of the other, or the other function and the derivative of the first. Now, generally speaking, when we use this rule, we rewrite it in a slightly different way. And the reason we do that is integration by parts is a method for converting an integral from one form into another. So we think of the left-hand side of this rule as being the format that we currently have. When we're looking at the integral of a product of two functions, then we need to think of one of them as being u and the other one as being dv by dx. In other words, already a derivative of something. And what parts does for us is allow us to split it into its component pieces and recombine it in such a way that we don't completely evaluate the integral, but what we do is convert it into a form that is a bit different. So instead of u and dv by dx inside the integral, we have v and du by dx. This is the integration by parts formula. And you'll be pleased to hear it appears in the formula book in exactly the same format that we've got here. Now, before we dive into some examples, let's take a closer look at the formula itself and see exactly what it does for us and what it doesn't do. Let's compare it to the product rule. It's very tempting to feel like every single time we come across an analogous result for integration that it's going to work exactly the same way as differentiation. So it's worth pointing out at this point the things that are similar and the things that are different about the two. To start with, product rule, u dv by dx plus v du by dx, its role is to allow us to differentiate the product of two or more functions. If you've got two functions that you know the derivatives of independently, then we can use product rule to find the derivative of the product of those two functions. Limitations, well, it doesn't really have any. You can apply product rule as many times as you like, and it doesn't get that much more complicated just because you're applying it to multiple terms within a product. It also combines well with chain rule, as we've seen before. Quotient rule, in fact, is just an efficient way of combining product rule and chain rule. Is it in the formula book? No. You're expected to remember product rule. Quotient rule is provided in the formula book because it's a little more involved and there's more things in it that you might mess up. But product rule you're expected to remember for yourself. On the other hand, integration by parts, the formula looks a little more complicated, and although it is derived directly from product rule, it is going to be a little bit harder to get in your head because you've got minus signs, you've got derivatives of v and of u kicking around in different places. The purpose is similar to with product rule. Product rule is for differentiating the product of two functions, and integration by parts is for integrating the product of two functions. Limitations. This is where it starts to get a little bit tricky. For a start, it doesn't actually give us the integral. all it does is convert the integral into an alternative form. And our hope is that this alternative form of integral is going to be easier to evaluate. This is nothing new. We had the same kind of thing with substitution. We found a way of rewriting our integral in a different format in the hopes that the new format of integral would be easier to directly evaluate. The one bit of silver lining in here is that the formula is provided in the formula book, so you can look it up, and I would recommend that you do, especially while you're learning. But as a routine process when you're doing exam questions, make sure if a formula is in the formula book that you have it to hand, because it's one of the most annoying ways to lose marks in a question, to misuse a formula that is right there provided for you. So let's try an example. Remember, integration by parts won't compute the integral for us, but it does let us convert it to a different one. So we're going to break that apart a little bit and see exactly what it means. Here's our first example, the integral of 3x minus 2 multiplied by sine x. This is the parts formula. I've color-coded it slightly so you can see the different pieces within it. And the most important bit to look at to begin with is the left-hand side. We can see we've got an integral there which involves two terms, u and dv by dx. And our first job is to identify within the original integral we're given which of those two terms is going to be u and which of them is going to be dv by dx. So if we make a decision for now, we'll talk about exactly how we choose later on. Let's say the first bit we see, 3x minus 2, is equal to u, and the second bit is going to be equal to dv by dx. Once we know those, we write them down explicitly. So we state those two things, u equals this, dv by dx equals that. And then if you look at the formula, you can see what else you're going to need. In addition to u, you're also going to need du by dx. And in addition to dv by dx, you're also going to need v. That appears in a couple of places. So the next thing we do is compute those. Now you've got to be a little bit careful here. And different people have different ways of writing out these terms. But all four terms must appear at some point because you're going to need them, and you're going to need them in the right order and in the right places. And you have to be very careful because part of it involves differentiating. When you're finding du by dx from u, you have to differentiate with respect to x. And part of it will involve integrating because dv by dx is sine x. And if we want v, we need to integrate with respect to x. So we've got to be very careful with that. One of the two terms in our product will end up being differentiated and the other one will end up being integrated. This is one of the reasons why you have to be careful when you choose which is which. We'll talk more about that in a moment. Once we've got all of those four terms, we can substitute them straight into the right-hand side of the formula. So we have u times v, 3x minus 2 multiplied by minus cos x. Take away the integral of v times du by dx. So you'll notice the integral we end up with is the two terms from the bottom row. These two bits we've got here. The original integral we had came from the top two terms. We were writing those down directly from our original integral. And the new integral is going to have two terms, one of which is the derivative of one of the original factors in the integral, and the other one will be the integral of one of the original factors. The next thing we do is we simplify things a little bit. So for instance, the minus sign that went along with the minus cos x near the beginning, I've brought that out of the minus cos x bracket, thrown it into the 3x minus 2 bracket to make life a bit nicer. And we've also got minus the integral of minus 3 cos x. So I've pulled out a minus sign and we've got plus the integral of 3 cos x. And now, as you can see, the integral we're dealing with is simple enough to do directly. We can say the integral of cos x is sine x, so the integral of 3 cos x is 3 sine x. And we're done. Don't forget the plus c at the end. So here's the key points. This is what you've got to look out for every time you apply integration by parts to a problem like this. You start by writing out the formula. It'll be in the formula book. I'll make sure I keep popping it up on the screen so you've got it easily to hand. If you've written it out in full, you are much less likely to misapply it or to forget which term goes where. The next thing you do is you state the values of u and dv by dx. So you look at the original integral and you choose which of the two terms is going to be u and which of them is going to be dv by dx. This also determines which one will be differentiated and which one will be integrated to form the new integral that you're producing. Then we evaluate du by dx and v. In other words, we apply that differentiation step and the integration step with each of the two separate functions in order to generate all of the terms we need to substitute into the formula. Then we do the substitution. Once we've done that, all that's left is some simplifying, and if we've done it correctly, we've chosen a suitable method for the integral at hand, we should have an integral that now we can evaluate directly. The next thing I want to look at is the type of questions that require integration by parts, and some similar questions where you might initially think that integration by parts is going to be useful, but it may be that either there's an easier method that will allow you to sort it out more quickly, or it might be that even integration by parts is not sufficient and you need some clever substitution or something else. So sometimes a nice simple substitution is quick and easy, and that can be more efficient than integration by parts. Other times it's easy to overlook the fact that we can sort out things like brackets. We can expand a set of brackets and then avoid the need for integration by parts. You've seen this sort of thing with product rule as well. If you're differentiating the product to two things, sometimes it's quicker just to expand out and simplify, rewrite the expression in a different form rather than attempt to use product rule to differentiate. Have a look at these three integrals. See if you can spot any alternative methods that you could use for these. All of them are currently written in a product form, so a function multiplied by a function. But for some of them, it's possible to rewrite in a different form or perhaps to use another method to integrate. All right, so the first one will yield quite nicely to a substitution because the derivative of 2 plus 5x squared appears in some form or other as a factor of the original integral. Yeah, we have a 7x in front instead of a 10x, but it's close enough that by multiplying and dividing by 7 by 10, we can sort that out a little bit. So a substitution like u equals 2 plus 5x squared will work very nicely for that one. The one on the right, this one, you're going to find it's much easier to simply expand the brackets. Yes, we've got a root x in front, but that's just x to the power of a half. So you can work through the bracket, multiply it out, and in a single line, you've ended up with an expression that can be integrated using year one techniques. The middle one is the one where there is nothing else particularly straightforward that we can find. A substitution won't work, because if you have something like u equals 3x, well, du by dx would be 3. The derivative of 3x might appear in there, but it's not going to help us cancel out the x term that's been multiplied by e to the 3x. So parts is going to be perfect for this type of question. We've got something linear multiplied by e to the power of 3x. And now I'm going to show you a few more examples. Sometimes we have a product of functions that cannot easily be dealt with using parts. All the three that I've shown you so far are integrals that can be solved using parts, but sometimes there are quicker methods. Of these four, only a couple of them will actually allow you to find an answer easily using integration by parts. Have a look, have a think, see if you can guess or predict which ones are going to work nicely using integration by parts. And if you want to pause the video for a bit longer, maybe have a stab at one or two of them. All right, let's have a look through these. The first one, cos x over x, or 1 over x times cos x, turns out this one's an impossible integral. So although it looks relatively straightforward, it looks similar to the one on the right, x sine x, what could be that different about 1 over x times a trig function? Well, it turns out quite a lot. This particular function is called a non-elementary integral. You can look up the Wikipedia article if you want to see a list of a few others, but there are all sorts of integrals that cannot be directly integrated to provide us with something involving elementary functions. In other words, the functions that you see on your scientific calculator, trig functions, exponentials, logs, powers of x, roots, that sort of thing. There is no answer to this integral using those functions. There is no combination of those functions that you can put together and differentiate to get cos x over x. The next one, x to the 5 times e to the x. Technically, you could break this apart using integration by parts, but I don't want to, because you would have to repeatedly apply the parts process. We'll look at that idea in detail later on, because occasionally you are requested to apply integration by parts more than once, but you are unlikely to be expected to apply it 5 times. All that does is waste time during the exam. You're not demonstrating any additional knowledge, you're just giving yourself more and more opportunities to make algebraic slips. So you're not going to get a question like this in the exam. The next two, perfect integration by parts questions. There is a linear term multiplied by an exponential, and there is a linear term multiplied by a trig function. One of the clues here is that the two functions involved don't play nicely together. There's no easy way to combine or simplify when you've got some kind of polynomial multiplied by a trig function, or some kind of polynomial multiplied by an exponential function. Similarly, if you've got a log and a quadratic, or you've got e to the x and cos x multiplied together, those functions are not sufficiently closely related that you could find any other easy way of dealing with the integral. So parts is going to be really useful for those. The next thing I want to share with you is a really nice way to think about the integration by parts process. Before you dive into putting functions into a formula, which can be quite a lot of work, it can be really helpful to have a quick, easy way of glancing at an integral and asking yourself what would happen if I integrated by parts, so that you can see if it's something you want to invest the time in doing. It should be possible, once you've got to grips with this idea, to glance at pretty much any question and tell yourself within a few moments whether or not integrating by parts is likely to be beneficial. So we just need the right perspective on it. Let me show you what I mean. If you apply the parts formula, you start out with an integral of the form u dv by dx, and you end up with an integral of the form v du by dx. There's other bits in the formula too. There's a uv term at the beginning, but what's interesting and important about it is what the integral involves, because the whole purpose of integration by parts is to take an integral that you cannot easily evaluate and rewrite it in a form that involves an integral that you can more easily evaluate. Essentially, what's happening here is one of your two original factors is being replaced with its derivative, u becomes du by dx, and the other one is being replaced by its integral, dv by dx becomes v. So with that in mind, the question becomes, how can you choose u and dv by dx to ensure that the new integral is simpler than the original integral? And if it's not possible to do that, then that's a good sign that your integral is unlikely to yield nicely to integration by parts. Doesn't necessarily mean that parts is completely out the window. There are a few sneaky examples that I'll show you towards the end where it may look hopeless, but there might be something clever you can do. But by and large, for the most standard integrals you'll deal with involving parts, you'll be able to see straight away that it's going to be a good idea by thinking about what happens when you replace one of the factors with its derivative and the other one with its integral. One nice way to think of this is in terms of polynomials. If you have a polynomial and you differentiate it, it gets simpler. It literally has an order which is one lower than it was. Quadratics become linear, linear terms become constant, and so on. Whereas if you integrate them, they generally get more complicated. Quadratics become cubic, cubics become quartic, and so on. So if you had two polynomials multiplied together and you applied integration by parts, then one of them would end up being simpler and one more complicated. Now, for a lot of functions, that's not exactly what happens. E to the x doesn't change its level of complexity no matter what you do to it. E to the x differentiates to e to the x and it integrates to e to the x. Trig functions, although they switch around between sine and cos, minus sine and minus cos, they don't ever get anywhere. They will go round and round in cycles. So although they never get simpler, the trade-off that we have is that they also never get more complicated. Let me show you with an example how this works. When you're looking at an integral like this, 4x minus 1 multiplied by sine x, the first thing you can ask yourself when you recognize you've got a product of two functions and they don't play nicely with each other is, well, would integration by parts be useful here? And you can look at the two separate factors and play out in your head what would happen if you replace one of them by its derivative and the other by its integral. Now for sine x, it doesn't really make any odds whether you replace it with its derivative or its integral, because either way it's going to involve cos x. The derivative of sine x is cos x, the integral of sine x is minus cos x. But for 4x minus 1, it does make a difference. Would you rather be dealing with an integral that has 4 times something involving cos x, or an integral that involves 2x squared minus x multiplied by something like cos x? I know which one I prefer. So in this case, it makes sense to replace 4x minus 1 with a 4 and to replace sine x with minus cos x. We get a much nicer looking integral which will involve something like 4 times cos x. Yeah, there's some minus signs going on, and remember you'll have the uv term in front, so it's not as if your integral just completely switches across to the other one, but the bit that you're interested in, the bit that you're concerned by that you need to now deal with, is the integral part of the integration by parts formula. Can you see what would happen if you chose 4x minus 1 to be dv by dx and sine x to be u? You'd still get a cos x, but your linear term would become quadratic, and you're essentially making the whole integral more complicated instead of less complicated. If you can turn it into the integral of 4 cos x, that becomes nice and straightforward. The next thing we're going to look at is a few common formats for these questions. You've already seen a few, and the more you look at, the more you'll start to recognize there are lots of things that a standard parts question will have in common with other standard parts questions. Generally speaking, it'll be a product of two functions that don't necessarily play nicely with each other, and very often you'll find that one of these is something linear. So to begin with, we're going to avoid the complexities of having sine of 3x minus 2, etc. We're going to have just an x in front and a something else after it. Give these a go. There are 5 questions here. Some of them will feel a little bit different to others. So if you've got into a bit of a groove and you think you've spotted a pattern, be alert for what happens when that pattern no longer works. Think carefully about the example we looked at last time. See if you can play out in your head what's going to happen before it happens. I'm going to give you a couple of clues in case you're a bit stuck on these before we run through them. And I'm not going to go through them all in detail, but I will tell you roughly how you should approach them. For the first 3, you should have no trouble if you let u equal x and let dv by dx equal the other bit. So x sine x will turn into something involving cos, because the derivative of x is 1 and the integral of sine involves cos x. Similarly, for the second one, if you set u equal to x and dv by dx equal to cos, you should be fine. And for the third one, again, u is going to equal x and the rest will sort itself out. The fourth one looks a little strange because it would appear that you've got 3 different things multiplied. But integration by parts is designed and set up for 2 things. And I'm not going to attempt to derive a 3-term integration by parts formula, mostly because it's not really necessary. If you want to integrate 3 terms separately, you could break it apart into x sec x multiplied by tan x, for instance, or even x times sec x tan x. If you really wanted, you could call it 1 times x sec x tan x, although that may not be particularly helpful for that one. You might find it works for some other examples, as we'll see in a bit. This one's a good example of a question where it really pays off if you have looked at and studied the standard results in the formula book. It's very tempting to think there's some results there that I can look up if I need them, but unless you recognize them when you spot them out in the wild, it's hard to know that you should look them up. If you see sec tan and you think, I'm sure I've seen that somewhere in a booklet before, then at least you've got a chance. You can then go and have a look in the formula book and identify what the derivative of it is, if that's what we're looking at, or maybe it's the integral of that we know. Whichever one you can find, have a look, and that might help you to see what's going to happen if you break it apart. But I'm pretty sure in this case, you'll find it works best if you have u equals x and dv by dx equals sec x tan x. Now the last one we're going to look at in a bit more detail in a moment, but to start with, I just want to point out that if you make u equal to x and dv by dx equal to ln x, you will either make a mistake or you will get stuck, because I haven't told you how to integrate ln x. I've not given you that result, we've not proved it, there's a reason for that, and we'll get to that on the next slide. In the meantime, for those of you who have completed some or all of these, you can check your answers using Wolfram Alpha. So all you need to do is type in the kind of thing that I've written here, integral of x sine x, integral of x e to the x. You can use the little hat symbol, which is shift and number 6 on a standard keyboard if you want to do powers, and Wolfram Alpha will usually understand pretty much what you mean when you type things in a logical way. Once you've done that, you can try a few of the questions from the book. 3A to C, questions 6 and 7 should all be suitable at this point. Now we're going to look at what happens when we have the natural log inside an integral. And the reason this might have tripped you up and confused you in the previous slide is that up until now, we haven't talked about what happens when you integrate ln x. We know how to differentiate it, but we haven't yet integrated it. It's just slipped through the cracks somehow. We've talked about trig results, we've looked at exponentials. Ln x has appeared in our table, but only as the integral of 1 over x, not as something which we know how to integrate. There's a reason for that. The reason is, in order to integrate ln x, you need to use integration by parts. Seems a little strange. You're going to see how that works in a moment. But in the meantime, we have to ask ourselves another question. Well, how can we deal with an integral involving ln x if, in order to find the integral of ln x, we need integration by parts? That seems like it's contradictory. Well, we have to get a little bit clever with it. But let's start with a parts question, which you might even have succeeded in for yourself on the last slide. And let's see what we did to skirt around the problem of not being able to integrate ln x. Because remember, one of the interesting things about integration by parts is that you don't necessarily need to be able to integrate each of the separate functions. When we did product rule with differentiation, you have to know the derivative of both of your factors in order to find the derivative of the product. With integration, that's no longer true. We need to know the derivative of one of the factors, and we need to know the integral of the other one. Which means just because we don't know the integral of ln x doesn't mean we can't evaluate x ln x. When we do our standard check, which one's going to be u, which one's going to be dv by dx, we no longer have a choice with this one. We'd like to say, let's make u equal to x so that it gets simpler and turns into 1 and everything becomes nicer like it did with x sine x or x e to the x. But we don't really have an option here because we don't know how to integrate ln x. So we're forced to integrate x and differentiate the ln. Well, let's set it up and we'll see what happens. U equals ln x and dv by dx equals x. When we differentiate ln x, we get 1 over x, and we're forced to have to integrate x, and we get x squared over 2. When we substitute that into the parts formula, which we can pull directly from the formula book, this is what we get. And this is why it works so nicely. uv out the front, ln x multiplied by x squared over 2, and then inside the integral that we've generated, we've got the x bit has become more complicated as we expected. X has become x squared over 2, but ln x has changed from being a function which doesn't play nicely with things like x or linear expressions. Suddenly it's something that does play nicely with those things. It's 1 over x. It can combine nicely with the x squared over 2 term. and things cancel out, and we get this lovely little integral. The bit at the beginning is just half x squared ln x, we've got that already, and the integral we're left with is simply the integral of x over 2. Nice and straightforward. Now this shows us two things. One, we can integrate things involving ln x without ever needing to know the integral of ln x. But also, because of the method by which this worked, because we ended up with 1 over x, which cancelled down nicely with the x squared over 2 term, hopefully you can see that x ln x is not the only thing we're able to integrate. We shouldn't have any problem with x cubed times ln x. You can probably imagine the kind of thing that's going to happen. X cubed can be integrated, you'll get x to the 4 over 4. ln x will be differentiated, we get 1 over x. And 1 over x, when we multiply it by x to the 4 over 4, will give us something which simplifies down nicely, give us something involving x cubed. We can even do it with stranger powers of x. It doesn't have to be polynomials, it could be other awkward powers of x. X to the half multiplied by ln x, not a problem. X to the minus 1 multiplied by ln x. So it may not look like a parts problem, ln x over x, but it essentially is. You can think of it as a power of x multiplied by ln x. This is probably a good moment to mention there is no commonly used alternative to quotient rule for integration. Generally speaking, there's no easy reverse process. If you have a fraction that you're trying to integrate, then if you can, you might try turning it into a product and using product rule. Remember, quotient rule is essentially a combination of product rule and chain rule. So the reverse of quotient rule is probably going to be a combination of integration by parts and maybe some substitutions. But just like parts doesn't always work very nicely, it's hard to get a fraction to always easily integrate. Generally speaking, unless you've got a nice particular fraction sort that you can work with well, you're likely to be stuck with a fraction. X to the n ln x is a good one to try if you feel confident with the others, because it shouldn't matter that we don't know the exact power. We should still be able to apply the integration and get a result involving n at the very end. And if you've done that one, see if you can do the integral of ln x. You'll need to think a little bit outside the box with this one, but if you've done the other 4 questions, particularly if you've done x to the n ln x, you might be able to use your result directly to calculate the integral of ln x. The next thing I want to look at is another example of an integral which involves ln x. This one is similar in terms of the method that you use to some of the others, but it's sufficiently different that when I looked at it just now in the book, I was a little bit stumped and I couldn't immediately see exactly how to break this apart. So I wouldn't be surprised if some of you are in the same boat. Now there's a couple of different ways to do this one, but I'm going to start by talking you through the process that I went through, and we'll see where we get stuck. Now the first thing to notice is that your natural instinct to write it as ln x multiplied by ln x immediately gets you a little bit stuck. It's not easy to integrate ln x. We can't readily break it into ln x times ln x because one of those factors will need to be differentiated, but the other one will need to be integrated. So what do we do? Well, how about we think of the two factors as being 1 and ln x squared. Feels like cheating. It's like asking someone what 48 divides by, and they tell you it divides by 1. Well, that's not going to help you to simplify a fraction like 16/48. But in this case, it's not necessarily as futile and trivial as it looks. We can differentiate ln x squared. We can just use some chain rule, and we can integrate 1. So at least we could give it a go and see where parts takes us. If we set u equal to ln x squared and dv by dx equal to 1, we can differentiate the thing on the left, we can integrate the thing on the right, and we get this. Remember, we're using chain rule here, so we're thinking of that ln x in a bracket squared as being something squared, which differentiates to 2 times the something. And then because the something wasn't just x, we also multiply by the derivative of the something. In this case, the derivative of ln x, which is 1 over x. Now if we put those together, remember we can check the formula book for integration by parts, substitute the values in. This is what we end up with. And you should notice that something cancels out. We've got an x and a 1 over x, so this integral does get a little nicer. But you may also notice that this integral is precisely the integral which we were complaining about at the beginning. We can't easily integrate ln x. So even if we decided to go down the route of setting u equal to ln x and dv by dx equal to ln x, we'd still be no worse off than we are now. We get stuck at the integral of ln x. There's no getting around it. We're going to have to find the integral of ln x in order to complete this question. But in fact, the trick that we used to get as far as we did with this question is going to help us to find the integral of ln x. Here's what I'm going to do. I'm going to label that integral j as opposed to I, so that I can work with it separately. I'll rule off and work on a separate side of the paper so that we can see more clearly what we're doing. And when we've got a result, we can bring it back in, substitute it in, and we won't have lost the flow of the question in the same way that you might if you were trying to do this all at once in one single column. So if j is the integral of ln x, and we've decided that we're going to think of it as 1 times ln x, then we're going to make ln x the thing we differentiate. We're going to make 1 the thing we integrate. And when we apply the integration by parts formula, we end up with this. uv minus the integral of v du by dx. And rather satisfyingly, just like we had before, there's an x on the bottom, there's an x on the top, they cancel out, but unlike the previous one, there is nothing else in the integral. So the whole thing reduces down to the integral of 1 with respect to x. Well, we know what that integrates to. We get x ln x minus x plus c. Now we can just take that result, substitute it right back in on the left-hand side, and we've got our answer. Just a quick point about the plus c. I've put it in grey on the right-hand side, and that's not because it shouldn't be there. In some sense, it should. But because if we're going to take that result and substitute it back into something different, there will be an additional constant of integration that comes into play at the very end. All we're going to do with this new integral j is multiply it by minus 2. So if you have a c from j, and you have another c, presumably you call them c1 and c2 because they're not necessarily the same, from I, then at the end you'll just have c2 minus 2 lots of c1. And since we don't care about what either of those are, we would just combine them and call it c. We can skip all of that, just take the raw integral without the constant and throw that straight in on the left, and everything will work just fine. We can simplify a bit here. We can certainly expand the bracket, and you might want to pull out x as a common factor if you feel like it, but it's not particularly essential. Now the only other thing I want to mention here is that sometimes graphs can be helpful for making sense of things. In the case of these kinds of complicated integrals, you might want to investigate what the shape of the curve looks like, and it may be helpful for you to get a sense of whether or not one looks like the integral of the other one, but they're not necessarily going to be hugely enlightening. For this example, we can identify which one's going to be the integral of what by thinking more easily, in fact, in terms of which one is the derivative of which. So we started with ln x squared and we integrated it. That means that if we look at the red graph and we differentiate it, we should get the blue graph. So start by looking at the red graph and think about the gradient and how it starts very, very steep positive and ends up plateauing at 0 gradient at a certain point, and then it starts to increase. While the blue graph follows that same pattern, but with its y coordinate rather than its gradient. Starts off very high, comes down to a 0, and then starts to gradually increase. There's a bunch more questions you can now try, quite a few of question 2. We did question 2D, that was the example I've just worked through. And you can also try question 4. Now, I'm going to look at some examples where integration by parts doesn't work. Sometimes you apply integration by parts and the integral that you produce does seem simpler, but it's still not simple enough. You've managed to reduce one complicated integral to another integral which is still complicated. Now, it's not always the case that if at first you don't succeed, you should completely give up, but in some cases it is. If you have applied integration by parts and what you've got is more complicated than what you started with, or if there is no way that you can see that it's going to eventually get better, then you should consider looking for a different approach. It might be that there's a good substitution you can apply, or you can break apart some fractions. But if you can see the light at the end of the tunnel, then you don't have to give up after one iteration of integration by parts. Have a go at these questions and hopefully you'll be able to build up a sense of what I mean. Try them in order. Do question 1 and then use question 1 to help you with question 2, and then use question 2 to help you with question 3. Be careful, it's very easy to make mistakes with some of these. I made many mistakes when I was going through these and had to keep going back to correct my plus and minus signs, getting fractions all over the place. So take care with your structure, but make sure as you're working through each question, you're taking advantage of the results that you've previously found. All right, let's go through some answers. For the first one, we should end up with an integral that looks something like this. This is taking u equal to x and dv by dx equal to sine 2x and applying the parts formula directly. Now that integral is something we can evaluate. Cos 2x we can integrate because cos becomes sine when you integrate. Cos 2x will become sine 2x over 2. So we end up with a positive quarter sine 2x. The two negatives cancel out, cos becomes positive sine, and then we divide by 2 because the derivative of 2x is 2. Now for the second one, if we apply the parts formula, again taking u equal to the x part, the x squared bit in this case, and dv by dx equal to cos 2x, the cos bit becomes something involving sine. The x squared bit reduces down to something involving x, but that's still not quite simple enough to evaluate directly. However, if you look carefully, you will notice this result is exactly the same result that you answered in question 1. So there's nothing stopping you from reusing the entire answer from question 1. It looks a little messy, but all we're doing is subtracting from half x squared sine 2x everything that we had written for our answer in question 1. The same kind of thing happens again in part 3. You will very rarely be expected to apply integration by parts more than twice, but you may well have to apply it twice. Generally, you'll be guided through, or there'll be an indication in the question. It might say, use integration by parts twice, which is usually a big clue. Or it might ask you to find the integral of x sine 2x for part A, and then ask you to find the integral of x squared cos 2x for part B. There's a question like that in the book. We again notice for this third one that the result is one that we've already calculated. So we can apply that. As you can see, it gets messier and messier the further you go. The potential for errors starts compounding and the interest will start to wane. So you want to try to avoid doing this kind of thing. If you think you're going to have to apply parts more than a couple of times, there may be a better way, or it may just be a question that you want to avoid. Have a go at this one though. Think about it before you dive in. See if you can work out how many times you'll need to apply integration by parts, and make sure your structure is clear. If you get to a point where you're stuck at a new integral that you can't deal with, then rule off and work separately on the new integral and then bring it back in afterwards, and you'll find that it's a lot less confusing than trying to keep track of an entire big expression with massive sets of brackets while you're trying to apply integration by parts. Then you can have a go at questions 3 and 5 from the textbook. The last bit I want to show you is a few challenge questions which are a really nice application of integration by parts. So you might enjoy these, and even if you don't want to work through them for yourself, I'd highly recommend you skim watch these bits so that you get a sense of what you might be able to do with integration by parts if you come across a question like this. It's not something you're likely to be tested on at A level, but it's a really useful idea to have in the back of your mind for some of the sneaky integrals you might come across during further maths or beyond. So occasionally we apply parts more than once to evaluate an integral, but in some cases all that happens is you go round in circles. These two challenge questions are two such problems. You can think about what will happen if you pick one of these things to integrate and one to differentiate, but because of the type of functions we're dealing with, we don't reduce down from x squared to x to a constant. E to the x just keeps going back to e to the x whether you're integrating or differentiating. Sine and cos just oscillate back and forth between cos and sine, minus cos, minus sine. So have a think and have a play around with these. When you're ready to come back to the video, I will show you the approach that works. It's really quite nice. All right, let's start with the first question. E to the x times cos x. Well, let's see what happens if we just dive straight in and try integration by parts. Let's see where we come unstuck. Let's use e to the x for the value of u, and cos x can be dv by dx. Shouldn't make much difference which way around you've done it, you'll get similar results. We can differentiate e to the x, nothing much changes. We can integrate cos x, we get sin x, because sin x differentiates to cos x. If you get mixed up, try working backwards and double check that you've got all your signs in the right places. Remember to look back at the formula and make sure we're applying this properly. We should get e to the x sin x minus the integral of e to the x sin x. In other words, the e to the x cos x integral that we had has been converted to something involving the integral of e to the x sin x. Okay, doesn't look much simpler. In fact, it's a very similar kind of integral to the one we started with, but it's different and it's just as difficult. Well, let's give it a name, because that's a good way of making sense of new things that we don't understand. And let's see what happens if we attempt to evaluate that integral using integration by parts. So we're not being put off by the fact that it doesn't seem to have worked. We can see that this might be taking us in circles, but we're going to plow ahead and do it anyway. U equals e to the x, dv by dx will be sin x this time. When we differentiate one and integrate the other one, we get this. Minus e to the x cos x plus the integral of e to the x cos x. Very, very similar to the last time, which is unsurprising. Sin x and cos x are very near cousins. Well, you can see what's happened. In order to get the integral of e to the x cos x, we need the integral of e to the x sin x. And in order to get the integral of e to the x sin x, we need the integral of e to the x cos x. So you're chasing a blue form, which you need in order to get the purple form, and you can't get the purple form until someone gives you the blue form. You're stuck in a catch-22 situation. Although, we're not stuck quite yet. We can rewrite this, remember, because the integral we're trying to find, I, is there as part of the definition of the new integral, j. Now look carefully at what we've got there. We have j in terms of I, and we have I in terms of j. And you might think that tells us nothing. We need j to get I, and we need I to get j, but we can't get I because we haven't got j, and we don't know j because we don't yet know I. Or we could say, this isn't anything new. Ever since you learned how to solve equations with x on both sides, you've been dealing with similar problems. You say, how can I find the value of x when 2 lots of x add 3 is equal to 5 lots of x minus 4? I need x to find 5x minus 4, and I need that to find 2 lots of x plus 3. We don't let it bother us. We just do a bit of rearranging, and we can still deal with them. Look what happens if we take j and substitute it directly into I. Now, it may look like an unhelpful circular definition, but that's not quite what we get. When you sort out those brackets, we have e to the x sin x plus e to the x cos x minus I. Now, sometimes when you apply something like this, everything cancels out and you get a valid but completely unhelpful statement like I equals I. But in this case, we didn't. We got I equals some algebra minus I. We can add I to both sides. Then we get 2I. You want to know how long the piece of string is? Double half its length. So if you want the integral I, we just have half of 2 lots of the integral I. And Bob's your uncle. I really like this approach. It jumps out of nowhere at you at the end. You feel like you're going in circles. It doesn't seem like it's going to work. But at the end of the day, because of the symmetry of the two arguments, it's almost like you've got simultaneous equations going on. One of your integrals is impossible without the other one, but both together, they allow you to calculate both of them. In fact, if you wanted, now you've got I, you could go back and calculate J, because J depends upon I. You'll get a very similar looking result. As you would expect, e to the x sine x is a very close cousin of e to the x cos x, so their integrals are going to be close cousins. Now for the second challenge. We've got the integral of sine x times cos x. And it doesn't really make much difference which one we choose to call u and which one we choose to call dv by dx. So let's start by setting u equal to sine x, dv by dx equal to cos x. And when we differentiate one of those and integrate the other one, we get a cos and a sine. We can pull the formula out of the formula book and substitute the terms in, and this is what we get. And almost straight away, something jumps out at us. We've got here cos x times sine x, which is exactly the integral we were trying to get in the first place. So we don't even need to apply integration by parts a second time. We just need to notice that if we apply integration by parts, we get a result which depends upon itself. My integral is equal to sine squared x minus my integral. Well, that's just a long-winded way of saying 2 lots of my integral is sine squared x. Therefore, my integral must be a half sine squared x plus a constant. So that's remarkably quick. At no point did we actually have to evaluate an integral. We just had to apply the integration by parts trick and recognize that the two integrals that we end up connecting together happen to be the same. It's a really elegant bit of sleight of hand. But we've got a bit of extra space left on the screen, so let's just, for the sake of argument, let's see what would happen if we set u equal to cos x and dv by dx equal to sine x instead. Should give the same sort of result. It's an equally valid method, and there's nothing in here that's going to come out wildly different. We get some negative signs in here when we differentiate and integrate those two functions, and when we apply the parts formula, we still get something remarkably similar. We get the integral that we started by trying to find as part of the integral we're trying to find. The only difference is we've got a cos squared x instead of a sine squared x. Or maybe that doesn't bother you much. You know that sine squared and cos squared are closely connected, but it should be a little bit concerning that a half sine squared x is not the same as minus a half cos squared x. They're not the same, so one of them must be wrong, right? Well, maybe not. These are the two curves. Which of them is correct? Well, the secret here is that the curves I've drawn are just examples of the two functions written down underneath. The blue curve is actually y equals a half sine squared x, and the green curve is y equals minus a half cos squared x, not minus a half cos squared x plus c. The plus c is crucial here, because that represents an arbitrary constant, which can be anything, any number that you add. If you think about it, all we're saying is, if you differentiate minus a half cos squared x plus a constant, you will get sine x times cos x. And that's just as true for differentiating a half sine squared x plus a constant. That will also give you sine x plus cos x. The gradients of these two curves match perfectly for every value of x, because one of them is just a vertical translation from the other. In fact, there's an entire family of curves. These are just a couple of curves, but any of these would be equally valid. All of them are the same function, just shifted up and down by different amounts. So really what's going on behind the scenes is that the plus c for the blue graph and the plus c for the green graph are just
not quite the same value of c. So if you want to draw the same curve, you would have a value of c for the blue one which is just off by a half compared to the value of c for the green one. You can see that half if you try rearranging so they look more similar to each other. A half sine squared x is equal to a half of 1 minus cos squared x. And out pops the half. The result is still the same up to a constant. So the two integrals give exactly the same result, give or take a different constant. In other words, although the algebra bit of it may be different, it doesn't mean that the integrals are wrong. They are perfectly compatible because they describe the same family of curves, just from a different perspective. And now finally, if you were asked to integrate this and nobody specified that you should use integration by parts, there's a slightly quicker method you could use. Maybe you notice that sin x cos x is very similar to one of the double angle formulae. 2 lots of sin x cos x is the same as sin 2x. So what we're looking at is the integral of a half of sin 2x. Well, sin integrates to minus cos, so sin 2x will give us minus cos 2x over 2. And we've got a third, again different looking solution, minus a quarter cos 2x plus c. Looks even more different than the others. But if we plot that graph, we find again it satisfies exactly the same criteria. It's just one of the same family of curves. And if you want to write out the cos 2x formula in terms of either sin squared x or cos squared x, then you can show that it is in fact equivalent to the two things below, give or take a constant. That is halfway between them. So depending on which one you turn it into, cos 2x in terms of sin squared x or cos 2x in terms of cos squared x, you can see why it's below one of the graphs and above the other one.